Number 1, how do solutions differ from compounds and from other mixtures? A solution can have varied composition. For example, a little bit of salt in water is still salt water, and a whole lot of salt in water is also salt water. Now, from other mixtures, solutions differ because, like a chocolate chip cookie is a mixture, it is not a solution. It's not a homogeneous mixture. 2, which of the principal characteristics of solutions can we see in the solution of potassium dichromate that's shown in Figure 1? Here's Figure 1, and here are my principal characteristics here at the bottom. So after the solution is mixed, it has the same composition at all points. We can see that. The physical state is typically the same as the solvent. Here we can see that there is liquid as the solvent and there is liquid in the solution, or as the solution. The components are dispersed on a molecular scale. So I can't see where the potassium dichromate starts and the water stops. It seems to be all mixed together. And the dissolved solute will not settle out or separate. I can only witness that if I have this on my lab bench and I watch it for a long period of time. So I'm not sure that we can witness that in this picture, but I do know that to be true. Now, the composition of the solution or the concentration of the components can be varied continuously. If I put just a little bit of this potassium dichromate in this water, I would still make an orange solution. I wouldn't necessarily make as bright of an orange solution. And if I add more, it's very possible that I would make an even darker solution. But again, without having it on my lab bench, I can't test that. Because I'm just looking at the image here, I'm not sure that I would count that particular quality. Number 3, when potassium nitrate is dissolved in water, the resulting solution is significantly colder than the water was originally. So is the dissolution endothermic or exothermic? This is endothermic. It's colder than it started with, so it's an endothermic process. What conclusions can you draw about the intermolecular attractions that are involved in this process? Well, that means, for it to be an endothermic process, that means that the interactions holding the potassium and the nitrate together are much stronger than the solvent-solute interaction. So because of that very strong interaction, the potassium nitrate is actually going to take some of the heat from the water in order to dissolve. Number 3, is the resulting solution an ideal solution? No. An ideal solution is when there would be no intermolecular forces between the solute and the solvent. Number 4, give an example of each of the following. A gas in a liquid. Well, the most common is carbon dioxide and water. So we see this in any of our carbonated beverages. A gas in a gas. The air you breathe is a gas in a gas. We have nitrogen, we have oxygen, we have helium in our air, but we can't see the different components in our air. A solid in a solid. Any jewelry is going to be a solid in a solid. It's very rare to have any jewelry made out of a pure metal. For example, platinum is typically stamped PT 950. That means it's 95% platinum and 5% something else. Now that something else can vary depending on the jeweler's alloy. Sometimes that's silver, sometimes it's gold, sometimes it's nickel, but it's 5% some other solid. Number 5, indicate the most important types of intermolecular interactions of each of the following solutions. So we're again referring back to Figure 1. So here's Figure 1 again. We have our potassium dichromate. That's an ionic compound. And then we have our water molecule. Now our water molecule will have hydrogen bonding, but because we have an ionic substance here, the hydrogen part of our bonding will be demoted is the word I want to use. I'm not sure that that's appropriate, but what we'll be looking at here is an ion dipole interaction because we have our ionic solute and our water molecule, which has a dipole moment. Number 2, we have nitrogen monoxide liquid in carbon monoxide liquid. Now remember how to draw the Lewis structures of these particular compounds. So if we have our carbon monoxide and our nitrogen monoxide, we have a polar molecule. These are both polar molecules. So we have dipole-dipole interactions here. 3, we have chlorine gas and bromine gas. Now, chlorine gas, 2 Cl's together. This is a non-polar gas. Remember, the definition of a pure non-polar covalent bond is a bond between 2 elements, 2 atoms of the same element. So because these are non-polar, this would be dispersion forces. This would create an ideal solution. Now, if we have hydrochloric acid, and that is aqueous, so it's in a solution, and benzene, liquid benzene, although the hydrochloric acid is polar and there is hydrogen bonding, if these two are going to be miscible, it's going to be based on the dispersion forces, because benzene will only have those dispersion forces. Between methanol and water, we would have hydrogen bonding. Remember, hydrogen bonding is a specific type of very strong dipole-dipole interaction. Number 6, predict whether each of the following substances will be more soluble in water, which is a polar solvent, or in a hydrocarbon, which is a non-polar solvent. Well, if you have a non-polar solute, then this would be soluble in a non-polar solvent. Isopropyl alcohol is going to be more soluble in water, in your polar solvent, because isopropyl alcohol is polar. Potassium bromide, being ionic, will also be more soluble in water than it will in a non-polar solvent. Remember the old adage that like will dissolve like, so you have to be able to tell what is polar and what is non-polar. Number 7, heat is released when some solutions form. Heat is absorbed when other solutions form. Provide a molecular explanation for the difference between these two types of spontaneous processes. To put it succinctly, if we're going to break weaker intermolecular forces and then form stronger ones, we will release heat. If we break stronger intermolecular forces and form weaker, we will absorb heat. Number 8, solutions of hydrogen in palladium may be formed by exposing palladium metal to hydrogen gas. The concentration of hydrogen in the palladium depends on the pressure of the gas applied, but in a more complex fashion that can be described by Henry's law. During certain conditions, 0.94 grams of hydrogen gas is dissolved in 215 grams of palladium metal. Determine the molarity of this solution. We're actually going to calculate all 3 different ways to determine or describe the concentration of this solution. So I'm going to start by calculating how many moles of my solute I have. So I'm going to take 0.94 grams of hydrogen gas, and I'm going to divide that by the molar mass of hydrogen gas. And I get 0.465 moles. Now, if I'm paying close attention to sig figs, I have my 2 significant digits on my measured quantity, 0.94 grams. So I really should only have my moles. In order to avoid some excessive rounding error, I'm going to leave 3 for now. Now, I'm also going to need to know how many, or what is the volume of my solution in total. So for the total solution, I have 215 grams of palladium plus my 0.94 grams of hydrogen gas. Now really, I should round that to 216 grams. Again, to avoid excessive rounding error, I'm going to use the entire thing. So this is 215.94 grams of my solution. I'm going to divide that by my density, which is 1.8 grams per, and this is centimeters cubed. Now a centimeter cubed, that's what we use to describe a solid solution, the volume of a solid, but a centimeter cubed is also considered a milliliter. If we're going to describe the molarity, I'm going to need the volume in milliliters. So when I do this arithmetic, I get 0.1199, and then I get a repeating 6, so 7. And that is actually in liters. I went and divided this by 1,000 in order to get liters, because I'm going to need liters in order to calculate my molarity. Now I'm going to start rounding a little because this is excessive. So I'm going to call this 120 milliliters or 0.12 liters. So in order to find my molarity, I need the moles You could use either the 6.5 or the 7. You should get the same value. So I have moles per liter. And I get a 3.9 when I only use 2 sig figs, 3.9 capital M molarity. For B, in order to find the molality, remember that molality is moles of solute, kilograms of solvent. In this case, we do not need the solution density, although it is given to us. So the moles of the solute, which we calculated up here, and the kilograms of the solvent. Now we're told we have 215 grams of our solvent. Divide that by 1,000 and you get 0.215 kilograms of my solvent. So 0.465 divided by 0.215, you get 2.16 or so. And we were going to round that to 2 significant digits because our mass of solute, which we use to calculate our moles, is 2 significant digits. So we would report 2.2 lowercase m molal unit. Now for number 3, in order to determine the percent mass of hydrogen atoms in this solution, we need the grams of the solute and we need the grams of the solution, not solvent, but solution. Then we're going to multiply that by 100. So the grams of my solute divided by the total grams of my solution. Again, I'm not going to round this one in order to avoid additional error. And then I get a 0.44%, if I keep my 2 sig figs, 0.44% of hydrogen.